We now start module 3 of chapter 8. The title of this module is Schwarz Lemma and its applications. In our last module, we proved Hurwitz theorem, which states that if f and g are analytic inside and on a simple closed contour C, and if mod g less than mod f on C, then f and f plus g have the same number of zeros inside C. In this module, as an application of Hurwitz theorem, we prove Hurwitz theorem. In complex analysis, we know that a mapping is called open mapping if it maps open sets into open sets. Here we prove open mapping theorem, which states that a non-constant analytic function maps open sets into open sets. We also prove that a non-constant analytic function maps a domain onto a domain. This theorem is one of the most important results in complex analysis. As an application of open mapping theorem, we show that if f is analytic in a domain and if one of real f or imaginary f or argument f or mod f is constant, then the function itself is a constant. After that, we will prove Schwarz Lemma, and we note that this Schwarz Lemma has a far-reaching implication on the function of complex variable. We also provide some examples relating to this module. We now go to our presentation. So, we now start Schwarz Lemma and its applications. So, first we prove Hurwitz theorem. This is an application of Hurwitz theorem. Let f and z be a sequence of analytic functions defined on a domain D such that f and z not equal to 0 for all z belongs to D and n equal to 1 to etc. Suppose that sequence f and z converges uniformly to a function f z on every compact subset of D. Then either f z is identically 0 or f z not equal to 0 for all z belongs to D. So, proof: suppose that f z is not identically 0 in D. We have to show that f z not equal to 0 for all z in D. If possible, we assume that there is some z0 belongs to D for which f of z0 equal to 0. As zeros of an analytic function are isolated, there is a deleted neighborhood of z0, namely n delta z0, in which the function f z is not 0. That is, f z not equal to 0 for z belongs to 0 less than mod z minus z0 less than delta, where delta is positive number. Let delta dash greater than 0 be such that delta dash is less than delta. Then f z not equal to 0 on the punctured disk 0 less than mod z minus z0 less than delta dash. Let C be the circle having center at z0 and radius delta dash, and epsilon equal to minimum mod f z, z belongs to C. C being a compact subset of D, the sequence f and z converges uniformly to f z on C. Therefore, given epsilon positive, there is a positive integer n such that for z belongs to C, modulus fnz minus fz is less than epsilon for all n greater than capital N. Noting that epsilon less or equal to mod fz whenever z belongs to C, from above we obtain modulus fnz minus fz is less than epsilon less or equal to mod fz for all n greater than n dashed and for all z on C. Hence, by Ch8 theorem, we can say that the functions fz and fnz minus fz plus fz, that is equal to fnz, have the same number of zeros inside C. By assumption, fz has a 0 at z0. Therefore, fnz must also have a 0 inside C, which is a contradiction to the hypothesis. Thus, we conclude that fz not equal to 0 for all z belongs to D unless the function is identically 0. This proves the theorem. So, another statement of Hurwitz theorem: let f and z be a sequence of functions analytic inside and on a simple closed contour C, and suppose that f and z converges uniformly to a function f z inside and on C. If f z has no zeros on C, then the number of zeros of f z inside C is equal to the number of zeros of f and z inside C for sufficiently large n. We now come to an important geometric property of analytic functions that arises when we consider them as mappings, that is, mapping regions in the complex plane to the complex plane. So, definition: a mapping in the complex plane is said to be an open mapping if it maps open sets into open sets. So, now we state open mapping theorem. A non-constant analytic function maps open sets onto open sets. So, proof: suppose that the function w equal to fz is analytic at z equal to z0. We have to show that the image of every sufficiently small neighborhood of z0 in the z plane contains a neighborhood of w0 equal to f of z0 in the w plane. We choose a positive number delta such that fz minus w0 is analytic in the disk mod z minus z0 less or equal to delta and contains no 0 on the circle mod z minus z0 equal to delta. Let M be the minimum of mod fz minus w0 on the circle mod z minus z0 equal to delta. We shall show that the image of the disk mod z minus z0 less than delta under fz contains the disk mod w minus w0 less than M. So, this is the picture. So, here we take a circle having center z0 and radius delta, and we show that the image of this disk in w plane contains in a region this. Let w1 be an arbitrary but fixed point in the disk modulus w minus w0 is less than M. Then on the circle mod z minus z0 equal to delta, we have modulus W0 minus W1 is less than m, less or equal to modulus Fz minus W0. Therefore, by Ch8 theorem, the functions Fz minus W0 and Fz minus W0 plus W0 minus W1, which is equal to Fz minus W1, has the same number of zeros in mod z minus z0 less than delta. Since the function Fz minus W0 has at least one zero at z0, the function Fz minus W1 has at least one zero. This means that Fz equal to W1 at least once. Since W1 is arbitrary, the image of the disk mod z minus z0 less than delta must contain all points in the disk mod W minus W0 less than m. This proves the theorem. So, corollary: a non-constant analytic function maps a domain onto a domain. We recall that a domain is an open connected set. Let Fz be a non-constant analytic function. We know that a continuous image of a connected set is connected. Also, in view of open mapping theorem, it follows that Fz maps an open set onto an open set. Thus, Fz being an analytic function is continuous, and hence the result follows. So, another corollary: if Fz is analytic and univalent in a domain D, then f dash z not equal to 0 in D. Proof: if possible, we assume that f dash z0 equal to 0 for some z0 belongs to D. Since Fz is analytic in D, it has a Taylor series expansion about z0 of the form Fz equal to summation n equal to 0 to infinity a n z minus z0 to the power n. Now, f dash z0 equal to 0 implies that a1 equal to 0, and hence Fz minus fz0 equal to summation n equal to 2 to infinity a n z minus z0 to the power n has a 0 of order k at z0, where k greater or equal to 2 is any integer. By hypothesis, Fz is univalent, and so Fz is a non-constant function. Obviously, Fz minus fz0 is analytic in D. Since the zeros of an analytic function are isolated, we can find a neighborhood modulus z minus z0 less or equal to delta, where delta is positive, in which Fz minus fz0 has no 0 except z0. Thus, Fz minus fz0 not equal to 0 on the circle mod z minus z0 equal to delta, and hence m equal to infimum modulus fz minus fz0 such that z belongs to mod z minus z0 equal to delta is positive. Then, for any complex number c 0 less than mod c less than m, we have mod c is less than mod fz minus fz0, that is mod fz minus fz0 minus c minus fz minus fz0 is less than mod fz minus fz0. So, by Ch8 theorem, fz minus fz0 minus c and fz minus fz0 have the same number of zeros inside mod z minus z0 equal to delta. Since fz minus fz0 has a 0 of order k and k greater or equal to 2 inside this circle, it therefore follows that fz minus fz0 minus c has 2 or more zeros inside this circle. This means that the equation fz equal to fz0 plus c is satisfied at 2 or more points. This contradicts the fact that f is univalent in D. Therefore, f dash z not equal to 0 for all points in D. This proves the corollary. So, another result, if fz is analytic and univalent in a domain D, then the inverse map z equal to f inverse w is analytic in FD. Since fz is analytic and univalent in D, by corollary 2 f dash z not equal to 0 in D. Let w0 be a fixed point in f of D. Then there exists a unique z0 belongs to D such that f of z0 equal to w0. Let f inverse be the inverse of f. Then for any w belongs to f of D, we have f inverse w minus f inverse w0 by w minus w0 is equal to z minus z0 by fz minus fz0 is well defined for all w in a deleted neighborhood of w0. Proceeding to the limit as w tends to w0, we obtain from above f inverse dash w0 equal to 1 by f dash z0. w0 belongs to fd being arbitrary, it follows from above that f inverse is analytic in f of D. This proves the result. Now we consider an example. Let f be analytic in a domain D. If any one of real f or imaginary f or mod f or argument f is constant, then show that f is constant. So, since any one of real f, imaginary f, mod f or argument f is constant, f of D would be a subset of either the real axis or the imaginary axis or a circle or a line with constant argument respectively. Since none of them forms an open set, by open mapping theorem it follows that f is constant. So far we have discussed about Hurwitz theorem, which is an application of Cauchy's theorem. We also prove open mapping theorem, which states that a non-constant analytic function maps open sets onto open sets. We also know that if f is analytic in a region mod z less or equal to R, and if mod fz less or equal to m for mod z less or equal to R, then mod fz less than m for mod z less than R, which is maximum modulus theorem. We now prove Schwarz Lemma, which is the generalization of maximum modulus theorem, and this lemma has an far reaching implication in the function of complex variable. At last we provide some examples. We now go to our presentation. So, if fz is non-constant analytic function in mod z less or equal to R and mod fz less or equal to m on mod z equal to R, then the maximum modulus principle says that mod fz less than m for mod z less than R. We now develop methods to improve this bound inside the disk. The result, let fz be analytic in mod z less than 1 with a 0 of order n at the origin. Suppose that mod fz less or equal to 1 for all z in mod z less than 1, then mod fz less or equal to mod z to the power n for mod z less than 1, and modulus fn 0, that is nth derivative of f at 0 is less or equal to factorial n. Further, equality holds in 1 for some z not equal to 0, or in 2 if and only if fz is of the form fz equal to c z to the power n, where mod c equal to 1. So, proof: since fz is analytic in mod z less than 1, by its Taylor's expansion we obtain fz equal to summation k equal to 0 to infinity a k z to the power k for mod z less than 1, where a k equal to kth derivative of f at 0 by factorial k. Also, fz has a 0 of order n at the origin, implies that f0 equal to f dash 0 equal to f double dash 0 equal to f n minus 1th derivative 0 equal to 0. So, from above we obtain fz equal to summation k equal to n to infinity a k z to the power k, and that is equal to nth derivative of f at 0 by factorial n z to the power n plus n plus 1th derivative of f at 0 by factorial n plus 1 z to the power n plus 1 plus etc. for mod z less than 1. For z equal to 0, 1 is the hypothesis. Let z not equal to 0. Then from above we obtain fz by z to the power n equal to nth derivative of f at 0 by factorial n plus n plus 1th derivative of f at 0 by factorial n plus 1 into z plus etc., where 0 less than mod z less than 1. The series on the right side converges for z equal to 0. Let us define gz equal to fz by z to the power n when z not equal to 0 and equal to nth derivative of f at 0 by factorial n when z equal to 0. Now, gz is analytic in mod z less than 1. Let C denote the circle mod z equal to r where 0 less than r less than 1. Then by the maximum modulus principle we have modulus gz less or equal to maximum over mod z equal to r mod of gz, which is equal to maximum over mod z equal to r mod of fz by z to the power n, which is less or equal to 1 by r to the power n, where mod z less or equal to r. The above inequality is true for all r less than 1. Therefore, letting r tends to 1, we obtain modulus fz by modulus z to the power n is less or equal to 1. That is, mod fz is less or equal to mod z to the power n. Since g of 0 equal to nth derivative of f at 0 by factorial n and mod g0 is less or equal to 1, we obtain 2. In case mod fz0 equal to mod z0 to the power n for some z0 in 0 less than mod z0 less than capital R, then g z0 equal to 1. It means that mod g attains its maximum at the interior point z0. This is only possible if gz is a constant, say gz equal to c, or fz equal to c z to the power n for some constant c with mod c equal to 1, which is number 3. The case nth derivative of f at 0 equal to factorial n can be proved similarly. This proves the theorem. So, now corollary: let fz be analytic in mod z less than capital R with a 0 of order n at the origin. Suppose that mod fz less or equal to m for all z in mod z less than capital R. Then mod fz less or equal to m into mod z to the power n by r to the power n for mod z less than r, and nth derivative of f at 0 modulus less or equal to m into factorial n by r. Further, equality holds in 4 for some z not equal to 0, or in 5 if and only if fz is of the form fz equal to m c z to the power n by r to the power n, where mod c equal to 1. So, another corollary, let fz be analytic in mod z minus z0 less than r with a 0 of order n at z0. Suppose that mod fz less or equal to m for all z in mod z minus z0 less than r. Then mod fz is less or equal to m into mod z minus z0 to the power n by r to the power n for mod z minus z0 less than r, and mod of nth derivative of f at z0 is less or equal to m into factorial n by r. Further, equality holds in 6 for some z not equal to z0, or in 7 if and only if fz is of the form fz equal to m c mod z minus z0 to the power n by r to the power n with mod c equal to 1. Now, we state some results. Let fz be analytic in mod z less than 1 and mod fz less or equal to 1 on mod z less than 1. Then modulus fz minus fz0 by 1 minus conjugate fz0 into fz less or equal to modulus z minus z0 by 1 minus z0 bar into z for any z z0 inside the unit disk mod z less than 1. Another result, let fz be analytic in mod z less than 1 and mod fz less or equal to 1 on mod z less than 1. Then number 1, mod fz is less or equal to mod f0 plus mod z by 1 plus mod f0 mod z, and number 2, mod f dash z is less or equal to 1 minus mod fz square by 1 minus mod z square. So, we consider an example. Suppose that fz is analytic for mod z less or equal to 1 such that mod fz less than 1 for mod z equal to 1, so that fz equal to z to the power n has exactly n solutions in mod z less than 1. So, let gz equal to minus z to the power n. For mod z equal to 1, we have mod fz less than 1 equal to mod of minus z to the power n equal to mod gz. Hence, by Hurwitz theorem, we can say that gz and fz plus gz, which is equal to fz minus z to the power n, has same number of zeros in mod z less than 1. Since gz has n zeros at origin, it follows that fz equal to z to the power n has exactly n solutions in mod z less than 1. So, another example, let f be analytic in mod z less than 1 such that mod fz less or equal to 1 and f of 1 by 3 equal to 0. Then estimate modulus f of 1 by 7. So, solution, since f is analytic in mod z less than 1 and mod fz less or equal to 1 for mod z less than 1, we have modulus fz minus fz0 by 1 minus fz0 bar fz is less or equal to modulus z minus z0 by 1 minus Z0 bar into Z for any Z and Z0 inside the unit disk mod Z less than 1. So, taking Z equal to 1 by 7 and Z0 equal to 1 by 3, we obtain from above modulus f of 1 by 7 minus f of 1 by 3 by 1 minus f of 1 by 3 conjugate into f of 1 by 7 is less or equal to modulus 1 by 7 minus 1 by 3 by 1 minus 1 by 21, and from this we obtain modulus f of 1 by 7 is less or equal to 1 by 5. From this module we came to know about Hurwitz theorem, which is an application of Cauchy's theorem. We also came to know about open mapping theorem. This theorem is one of the important theorem in complex analysis. We also discussed about Schwarz Lemma, and this result has an far-reaching implication in complex analysis. We also discussed some examples relating to this module. For more problems, you can see self-assessment part of this module. You also discuss any reference books for more details. This ends module 3 of chapter 8.